I'm Hillary and I'm a software developer here at AWS. I work for our worldwide public sector organization and I've been at Amazon for about 3 years now. I've been interviewing for 2 of those years, and so today I'm going to be helping you out with your data structures and algorithms interview prep. I'm going to be talking to you today about the data structures and algorithms portion of our interviews here at Amazon. And I want to start this section by saying that we as interviewers are fully aware that being asked to write some code on the fly can be a little bit intimidating. And throughout this portion, I'm not so much going to tell you all of the data structures and algorithms that you must know. What I would really like to do instead is give you approaches on how to look at the problems, how to solve the problems, how to talk through the problems with your interviewer. Remember that when we're asking for you to write some code during an interview, we're not looking for you to be an encyclopedia of every computer science concept that's ever been. What we're looking for is humans and engineers. So we actually want to be able to talk to you about this problem and make sure that you understand the fundamentals for how to solve it. So to start, these are our contents. First, what is problem solving and where do data structures and algorithms fit in? Second, what are the common problem solving techniques? Third, how to prepare for the coding interviews. Fourth, coding interview tips. And finally, we're going to end the session with a little example. First, what's problem solving and where do data structures and algorithms fit in? So you'll hear interviewers talk a little bit about problem solving interview questions. You'll also hear interviewers talk about data structures and algorithms interview questions. And it can be really natural to think, okay, well, aren't those the same thing? We see those a little bit differently. And basically the way I think of the distinction is this. Problem solving can be for anyone and it can be about anything. Everybody solves problems in their day-to-day. However, not everybody uses data structures and algorithms to solve their problems. So I think of problem solving as the baseline of what we're doing, taking a problem and trying to solve it. I think of data structures and algorithms as tools that we use to solve the problem. So when you approach a data structures and algorithms problem solving type question in your interview, you can start by thinking of some of these questions. Which data structures and algorithms do you know? What are they used for, and how would you apply them to problem-solving questions? How would you find discussing these data structures and algorithms to be difficult? What would you find difficult about discussing these and then applying them to the problems? So let's talk about some common problem-solving techniques. And again, here we're talking more about problem solving. Problem solving are things that everyone can do, whether or not they're a computer scientist. They're kind of more fundamental techniques. So there's brute force. That's a problem solving technique, to just keep trying different ways to solve the problem until we've got it solved. There's the use of a data structure. That's one approach that we can use to solve a problem, and sometimes using the right data structure is the exact correct approach to solving the problem. String manipulation. So basically, if we're thinking about problem solving in a technical context, there are several different approaches we can use that involve string manipulation. You can use dynamic programming to solve a problem. And I know that particular phrase can be a bit of a buzzword for some people. Some people look at that and think, ooh, gosh, like I don't know anything about dynamic programming. I am not prepared for this interview. But that's not the case. Dynamic programming is essentially just a fancier way to say brute force, smarter brute force. So we are going to talk about that just a little bit later. And then finally, there's a divide and conquer problem solving technique. Again, I want to emphasize that these are not every problem solving techniques that exist. There are many more. This is just a small section of what you might encounter on your problem-solving related interview questions. So let's talk about brute force. Brute force is a problem-solving technique when the only solution, or maybe the best solution, is try all possibilities and choose the best between them. So an example here is implementing a Sudoku solver. So if you've ever tried to write code that does this, one of the ways you can do it is just basically guess and check. So guess a number that'll go into the first empty box and then try all permutations of the Sudoku puzzle with that first guess. If you find a solution with that first guess, fantastic. If not, roll back and try again. Try every possible permutation. That's a brute force technique. Use of a data structure. This problem-solving technique occurs when the most optimal solution is simply just picking the correct data structure and then writing basic driver code which utilizes that data structure. So a common theme when you're thinking about data structure-oriented problems is efficiency and big O efficiency. So for instance, you'll see a lot of examples where you might use a hash map to reduce data lookup to O of 1. The example that we've given on the bottom is this. Given an unsorted array of numbers, find two elements that sum to k. Now, a naive approach might be to iterate through the list, and then for every iteration, look through the rest of the list to see if any number in the rest of the list sums up to k with the number on your current iteration. This technique would work and would give us a correct solution, but it's not very efficient. We're looking at an O of n squared solution. If we apply a data structure to this problem, we can get it to be much more efficient. If we apply, say, a hash map, what we can do is only iterate through our array once, rather than in O of n squared time, we would end up with a solution that's O of n time, which is much better. So we could look through our array, and for every index in the array, take that number and put it in as the key to a hash map. The key to the map is the number that we found, and the value is k minus that number. When we get the number that makes up the difference between our current index value and k, we can look through the map to see if that key already exists in the map. If it does, that means that there's a number that we've already seen in a previous iteration of the array that sums up to k with the number we're currently on. Now that's probably easier understood by writing out the code and really getting your hands dirty, so I encourage you to do that and see how we can reduce this solution from an O of n squared solution to an O of n solution simply by applying a data structure. String manipulation. So this is kind of its own category of problem rather than a technique. Typically, the kind of problems we see here are one where we're given some string with some characteristics and we need to find or check something that fulfills certain conditions. So the example we're given here, given a string containing parentheses characters, validate that it's a balanced expression of parentheses. Now, I really like this example because not only does it dig into string manipulation type problems, but it's also a really nice example of a time that we can look at the problem and step back and think, what questions might we want to ask our interviewer to better be able to understand how to solve this problem? And that's a theme that I'm going to touch on throughout the rest of my presentation here, is that truly understanding your problem is the foundation to solving any of your coding interview questions. So in this case, in order to understand this problem, we might want to ask our interviewer things like, what does a balanced expression of parentheses mean? I would assume it means every open parenthesis has a closed parenthesis. Is that the case? We might want to ask them, what types of parentheses can I expect? Will it strictly be parentheses? Maybe am I looking for curly braces, square braces, anything like that? And having those conversations with the interviewer would help me as a person interviewing understand the problem a little bit better and be able to solve it a little bit better. To apply string manipulation to this problem, we just need to be able to take the given string, break it apart into pieces, and actually apply the little tokens in the string to be able to solve this problem. Now, I see, looking at this question, you might also be thinking of another technique that we talked about earlier. Perhaps there's an appropriate data structure that we could apply to solve this problem. I'll leave that as an exercise to you, but when you're looking at solving this problem, think about some of the problem-solving techniques that we've already discussed. Are there data structures that would help us in solving this problem? What string manipulation techniques would we use to solve this problem? What types of questions would we ask the interviewer, and so on? Next up, that scary word, dynamic programming. Now, basically, dynamic programming is simply an optimized brute force solution. So the idea here is that we have a brute force solution that tries every possible permutation of outcomes, but the dynamic programming component of this means that we store some of those previously computed outcomes. So we're optimizing our brute force solution by not necessarily having to calculate every permutation every time we need it. That's all it is. You won't very likely get an interview where your interviewer sits down and says, I need you to use dynamic programming for this. It's just a good technique to have in your back pocket and to understand so you can talk about why it might be appropriate or why it might not be appropriate. So the example we have here is to compute the Fibonacci sequence for a given n. For those who aren't familiar with the Fibonacci sequence, the basic idea is that every two subsequent numbers add up to the following number. So we've got 0 and 1 adds up to 1, 1 and 1 adds up to 2, 2 and 1 adds up to 3, and so on. If we were in an interview situation and we were given this question to compute the Fibonacci sequence for a given n and we weren't familiar with the Fibonacci sequence, that could be a great question to ask our interviewer. Remember that even in your technical portions of your interviews, your interviewer not only wants you to succeed, but they're there to be a teammate for you and to answer questions for you. We're not here to catch you out on phrases or terms or concepts that you don't understand. If you have questions or if you're not familiar with something, we would be happy to answer those questions. So a common way to compute the Fibonacci sequence for a given n is to calculate the Fibonacci sequence for the two numbers before n, because as we said, the two numbers before n in the series add up to n. So as the diagram shows here, this is kind of a recursive breakdown of the problem. So for f of 6, so this function with n being 6, what we want is to calculate f of 5 and f of 4 and add those two together. If we did the full recursive loop here, when we calculate f of 4, we calculate f of 2 and f of 3. When we calculate f2, we calculate f0, f1, and so on. However, if we were doing a dynamic programming solution instead, every time we calculate f1, we would store it somewhere. And so then next time I need f1, I don't need to calculate it again. I just look up where it's stored. And similar with f2, I need f0 and f1. Those are hopefully already stored somewhere. So I just pull those numbers rather than recomputing. And then it kind of rolls its way up. And so as you can see, by the time we get to f4, f5, and so on, we can just look up the resulting numbers that would build together to create f4, f3, f5, and so on. We can just kind of cross out all of these to represent that we're not actually doing those calculations anymore. We can just look them up. So that's the idea of dynamic programming. But again, don't feel like you need to go into an interview and say things like, I'm going to use dynamic programming to solve this. As long as you're able to talk through the pros and cons of storing a pre-computed answer versus computing again, that shows your interviewer you know how to think about this type of thing, and that can be just as powerful as knowing the actual words for it. So let's talk about the divide and conquer technique. The idea here is that you're dividing the problem into smaller ones, solving them independently, and then constructing the solution by combining the various sub-problems. And I want to talk about the divide and conquer technique in a couple of different contexts. One is that there's definitely technical approaches that we can take when we talk about the divide and conquer technique. The most probably well-known approach is the example that we're given here. Implement a method that combines two sorted arrays. So we can see with this little animation on the side, we're using a divide and conquer technique to sort two sorted arrays. And people who are well familiar with this will recognize this sort algorithm as merge sort. Very popular implementation that uses a divide and conquer methodology. I also want to talk about divide and conquer in terms of approaching any interview problem. Sometimes you'll be met with an interview problem that's just not necessarily technically appropriate for divide and conquer, but the problem space itself is appropriate for dividing and conquering so that you can solve it in the time allotted. An example for this would be if you're given some really complex problem with lots of different customer needs that you need to answer for, divide and conquer is a great way to approach the problem. Think about dividing it into smaller subtasks, maybe one customer requirement at a time, and solving each of those subtasks to create a bigger solution that's made up of your solution to the various subproblems. So again, those are just a few problem-solving techniques to keep in mind when you're doing your coding interview. It's by no means a comprehensive list. That was just to give you a little flavor of things that you may want to be familiar with, may want to brush up on, and may want to be able to have a conversation about with your interviewer, even if it's just asking questions or saying, I'm less familiar with that, maybe we could try this approach instead. Have those conversations with your interviewer. So now let's talk a little bit about what you can expect from your interview. First, we're not going to ask you something that requires background in fields other than software engineering. I do want to say a small caveat to this is that if you're applying for an EC2 team where you're going to be doing a lot of hardware component level programming, you may be expected to know some of the lower level fundamentals, but you should be well aware of those expectations before you go into the interview. Beyond those really specific cases and pretty rare cases, if you're interviewing for a software development engineering position at Amazon or at AWS, we won't be expecting background in fields other than software engineering. We're also not going to ask you trick questions, and this is one that I personally really believe in. I don't think that we should be treating interviews as an exam, and lots of people that I've talked to at Amazon, certainly most of the interviewers that I've worked with, believe the same. This isn't an exam. This isn't here to catch you out on things that you might know. We're not here to ask you trick questions. We're here to evaluate what you know. And in order to evaluate what you know, we want to set you up for success, and that means not asking trick questions. We're not going to expect you to know niche domain-specific knowledge for an SDE position. This is awfully similar to that first bullet point, and basically it even applies to different computer science fundamentals. If you don't know a really niche computer science concept by name, or even if there's an algorithm that you've never worked with before, or maybe your interviewer mentioned some sort of data structure that you've not heard of, we don't expect you to know absolutely everything. Like I mentioned earlier, we want to hire humans, not encyclopedias. And so if there's some domain-specific knowledge that's outside of tech, we're not going to expect you to know that. And even if there's some niche knowledge within tech, feel free to ask questions. Feel free to have a conversation with your interviewer about it. We don't expect you to know everything. We will expect you to be able to communicate your ideas and to explain your solution for the given problem. This is absolutely critical, particularly because you only have a limited amount of time in these interviews. And if you run out of time when you're solving a problem, that's not necessarily a bad thing. And in some cases, it can indicate a good thing. Your interviewer will have follow-up questions. If you solve the initial problem really quickly, we will ask follow-up questions to kind of keep pushing the limits of the data that we can get out of you as a candidate. We want to know as much about you as possible, and so we'll keep asking questions as long as we have time for you to keep answering them. So that said, it's very likely you will get to a point where you don't finish a solution. And if you weren't communicating your ideas throughout your problem solving, we might not really know where you're going with this unfinished solution. It's so critical to be able to communicate your ideas throughout, so we're following your train of thought, and we're not just looking for one perfect last solution, we're looking for your train of thought throughout. We expect you to write code during the coding interview. So yes, we expect you to actually write code. We expect you to be familiar with syntax. We expect you to be familiar with your chosen language. Your interviewers also know and understand that if it were the real world, you would have a compiler, you would have an IDE to help you catch little syntax mistakes, things like that. So don't panic too much about if you missed a semicolon somewhere, but we do expect you to write code that looks like code and reads like code. We expect you to deal with ambiguity, and so this goes back to what I was saying earlier. A huge part of problem solving is being able to ask questions to understand the problem that you're trying to solve. Sometimes we'll ask an intentionally ambiguous question, and we expect you to be able to talk through your thoughts about the problem, to ask questions to eliminate some of that ambiguity, and to solve the problem appropriately based on the questions and understanding that you gain. We expect you to write code that's readable, maintainable, and testable. So I covered this a little bit earlier, and basically the idea here is the same. We do expect you to write code that is legible, that we can read and understand. You will have been communicating your ideas throughout, so maybe if there's one part that's a bit less clear from reading the code, we might still understand your idea from the way you communicated about it. But you do want to be able to write code that we can look back at afterward and still kind of see your train of thought. We expect you to identify the time and space complexity of your solution, so be prepared for that. Know your big O complexity. We expect you to talk about alternatives if you can think of any. Particularly when we're talking about data structures and algorithms, we want to know that you're able to think about trade-offs between different choices you can make. So for instance, if you're solving a problem, why might you choose a fixed size array versus a more dynamically sized list? Why might you choose a hash map rather than some sort of sorted tree map or something like that? We expect you to be able to talk about alternatives and talk about those trade-offs. A couple of tips for your coding interview. First, it's fine to start with a suboptimal solution. Don't try to start with the perfect approach and freeze. We see this with candidates from time to time, is that they try to over-optimize in the beginning and then they just never quite get off the ground because they weren't comfortable starting with a solution that was maybe suboptimal, but would get the conversation started and would get their brain kind of moving in the right direction. It's fine to start with a suboptimal solution. It gives your interviewer the chance to see you iterate and talk about things that maybe you know are suboptimal, especially if you can vocalize that and say, I'm going to start with this. I know it's suboptimal because of this, but maybe later I'll have time to try this. That's an amazing way to see a candidate's train of thought. Having a solution that's not optimal but solves the problem is better than no solution. So this goes a lot with the top bullet point. If you have a solution that's well thought through and you've talked me through the pros and cons and you understand the pitfalls of it, and it's not optimal, but it solves the problem, that's much better than having no solution at all. Again, communicate the thought process with your interviewer. This is critical. We want to be able to see your thought process. We want to be able to see how you problem solve, see how you make trade-offs, see how you iterate through a problem to ultimately find a solution. And communication is really key for that. We want to gather as much data as we can about you as a candidate, but unfortunately we can't read your mind, so we really need you to communicate your thought process with us. And finally, ask your interviewer for help if you get completely stuck. We're people and we want to see you succeed. We want to see you have a positive interview experience and do well. If you're stuck, that's not helpful for you as a candidate or us as interviewers if we just sit there and let you struggle. Nobody's enjoying that. Nobody's learning about each other through that. And so it is perfectly fine to ask your interviewer for help. So now I'm going to walk us through an example as if this is an interview and I am the one being interviewed. So the example is this. In this problem, we will focus on coding an in-memory caching component for an existing system. Your task is to implement a least recently used, or LRU, cache. Now, let's say as an interviewee, I'm not super familiar with an LRU cache. That would be a perfectly appropriate question to ask my interviewer. I could say, could you define an LRU cache for me so I can better understand how to implement it? So here we've got the basic definition of an LRU cache. It's a data structure of fixed initial capacity n, and if at any moment it's asked to add the n+1th item, it will remove the least recently used item to accommodate the new one. So now if I think back to my problem-solving techniques earlier, one of the techniques that I talked about was divide and conquer. So I've got this big problem, implement a cache. Oof, seems like a lot. If I divide that into smaller sub-problems, it seems a lot more reasonable. So instead of thinking about the problem as a whole, let's start thinking about specific operations that I need to support. There's the get operation that returns the value if a given key exists in the cache, and there's an insert operation that inserts the given key value pair to the cache. Now, depending on how the problem is structured, maybe my interviewer gave me these operations initially, or maybe this is something that I could have talked to my interviewer about in the beginning and asked a question like, what operations should I intend to support? Or even saying, Now, knowing what I know about caches, I think I'll need to support a get and an insert operation. What do you think? Those would be perfectly appropriate questions. Now let's say as an interviewee, I don't really know where to start and I don't know how to start building the perfect LRU cache solution. And so instead of getting frozen trying to think of that perfect gold star solution, I'm going to start with something a little bit simpler. I'm going to take a step back and solve a simpler version of the problem first to give my interviewer a chance to see my problem solving without needing to come up with the perfect solution right away. So I'm going to start thinking about what would a solution look like if there's no eviction policy. Now, your gears might already be turning about what a solution here would look like, and I think the optimal solution is very simple, and it just boils down to using the correct data structure. So in this case, I'm going to use a hash map, and both operations can be done in O of 1. So here's the code I'm going to write for my interview. I'm creating a new hash map called cache, and then the get checks if my map contains the key. If it does, return the key. Otherwise, let's say I throw an exception. This is another good area to talk to your interviewer about. Talk about the benefits of throwing an exception versus maybe returning some sort of value there. For insert, I'm going to simply put the key value pair into my map. So now, if I think about the pros and cons of this solution, the pros, it's incredibly efficient. We've got O of 1 complexity for both get and insert. Fantastic. Cons, of course, it doesn't actually solve the problem. We don't have any eviction policy yet. So I could talk to my interviewer about the pros and cons of this solution, and right away they get an idea of me as a candidate, that I understand how to use a hash map. I understand what to do if the item is not contained in the map. I've maybe talked through what I think about throwing different exceptions. They already get a bit of an idea of who I am as a candidate, even though I haven't built out the perfect solution. But let's carry on with a slightly closer solution to what we're actually looking for. So approach 1, limiting cache size. So how do we adapt our initial approach into an actual true LRU cache that evicts old entries when the cache is full? And what's the cost of this eviction? So let's say in my approach 1 here, I want to keep a sorted list of entries. When I reach the cache's capacity, I'm going to remove the oldest list entry. So now if I modify my solution, I might end up with something like this. I've got some sort of maximum size, and instead of having a hash map, I now have a list of cache nodes. And this cache node, in the example here, it's just kind of written out. I wouldn't necessarily want to create some sort of object like the cache node without taking a second to explain what I intend it to be to my interviewer. So I might even write a comment like this one above. Cache node has fields, key, and value. And I would take a second to explain to my interviewer why I think it's necessary, why I think it might be useful, and so on. So now, what does my get operation look like? I get a key, and so now for each cache node in my cache list, if the key of the node that I'm looking at equals the key that I'm looking for, I'm going to get the value, insert the new key value pair, and return the value. My insert, I'm going to remove the key from my list, and now if my cache size is equal to my maximum size, I'm going to remove the thing at item 0. And finally, I can add my new cache node with the key value pair to the list. So now, why does this work for eviction appropriately in an LRU cache way so that the least recently used item is removed? The reason I know I can do this is because the way that I'm adding new things is appending to the end of the list. So that means I'm always appending to the end, so my least recently used item is going to be the thing at the beginning. Because if I find the key, I'm removing it and then appending it to the end. So basically, if you're a visual thinker, you can imagine taking a list of things, slipping something out of the list, tacking it onto the end with the new value. Our oldest thing is always going to be at the front of the list. So I would talk to my interviewer about the pros and cons of this solution. One of the issues with it is it's awfully slow. So if we think about that initial insert, we're going to need to remove, we're going to need to check, and then we're going to need to add. And we need to think about the complexity of each of those operations. For our get, we need to iterate through the entire list in order to get the key. So both operations are done in O of n time, and space complexity is also n, where n is the size of the cache. So at this point, as an interviewee, as a candidate, I might think, what can I do better? So here's an idea. Let's focus on making the read cheaper, and we'll call this approach 2, better read operations. Now, this would give me a fantastic opportunity to talk to the interviewer about the context that my cache might live in. Remember that at the end of the day, we're trying to solve a problem, and a cache is never just a cache. It's also the context that it lives in. Maybe this cache is for a website where reads need to be incredibly fast, but writes can take a little bit longer because they're done asynchronously, something like that. So let's say that that's the case, and we just need to make our reads really cheap. The idea is that we'll delay any mutations until the next insert. We do that by maintaining a stack with all the recent queries and a map for quick access to values. So here's what that solution might look like. So now I've got a map of integer to integer, that is my cache, that's going to be keys and values, and a stack of integers, which is my recent keys. So when I'm looking to get the key, remember I want the get, the read, to be really fast. So at this point, I'm just looking at my list. If the cache contains my key, that's an O of 1 operation. Recent keys, push, key. So that means I've seen this key recently, I'm going to push that key onto my list of recent keys. And then return the key from the cache. If it's not contained in the cache, then again, we throw an exception or something like that. So great, we've got this get operation that's a nice O of 1. Our insert looks like this. If the key is already there, or if the cache is not full, so if cache contains the key, or cache size is less than the max size, we can insert like this. Push the key onto recent keys, because it's a key that we've recently seen, and then put into the cache map the key to the value. Something that we might want to talk to our interviewer about is the semantics of our chosen language. If we put onto a map a key that already exists, if we use the syntax of put key to value, does it update the existing value? Does it try to add a duplicate key, which might not make any sense? So we would just want to be able to talk through the semantics of our chosen language there and make sure that we understand and are able to talk through what's going on. And then let's say we've got this insert and rebuild cache for the case where the cache doesn't initially contain the key, or maybe the cache size is at max size. But rebuilding the cache, that's going to be a pretty sticky and expensive operation. We'll need to rebuild the cache, which is now an O of n. So I would talk to my interviewer about the pros and cons of this solution. So some of the pros, we've got a really fast get, and in some contexts, that would be perfectly enough. But some of the cons, we still have kind of an expensive insert operation here. And we might even talk about the con that we're using two separate data structures, but that's not necessarily seen as a con. Maybe you might want to talk about the additional complexity that introduces, the additional space. But if it's the right choice, then it's the right choice. It's still something that you could talk to your interviewer about. So let's look at a third and final approach. So we're going to explore a solution where the two operations are in O of 1 time complexity. That's fantastic. O of 1, that's the, kind of ideal, what we're looking for. So we're going to use a hash map and a sorted linked list. We can push onto the front and end of a linked list in O of 1, and we can add to a hash map also in O of 1. So here's what the code for this could look like. We're still using our cache nodes from before. We've still got our max size from before. Now we've got an integer to a cache node, and we've got pointers to a cache node at the head and tail of a linked list. So our get looks like this. We check if the cache contains the key. If it does, get the value for that key, and move node to head. And that node represents the key value pair in the cache. Finally, we're going to return head.getValue. So we've just moved the node that we most recently used to the head of our list. So when we get head.getValue, that's an O of 1 operation. We're getting the first value that's associated with the node and the key that we asked for. Now insert looks like this. If the cache contains the key, get the value for that key, set the value of the cache node to that value, the given value, and again, move node to head. So you'll see this pattern of moving node to head. So basically we're constantly saying, move the node of what I just looked at to the head of my linked list. That's an O of 1 operation to move around things in a linked list. And so we bring it up to the front of the cache. So it's our most recently used thing. If it's not contained in the cache, it's a brand new key value pair, we're going to create a new cache node with that key value. We push on the new node, and then we also put it into the cache. If the cache size is greater than the max size, we can remove the node at the tail. So we need to do two things in order to do that. Remove it from the cache and remove it from the list that indicates what's been most recently used. So for the cache, that map, we can say cache.remove tail.getKey. So that's remove the key and the key value pair related to the last thing in our ordered list. And then tail equals tail.next. That's essentially just moving the reference to the next thing in the list and essentially removing that last node in the list. So again, our insert operation becomes O of 1. I would talk through the pros and cons of this with my interviewer. Also, for me, I'm a very visual person, and it's something that makes remote interviewing a little bit more challenging for me, is that if I were solving this problem, I would want to draw out some nodes with various pointers on paper, maybe walk through a couple of examples, and make sure that I'm not leaving any edge cases or dropped any particular bit of code or node pointer update. And that's the next step I would take, to walk through my logic, make sure that I'm not missing any edge cases, and also to make sure that my interviewer understands my logic as well. If you're interviewing in person, obviously you could do this on a whiteboard. If you're interviewing remotely, feel free to try to write it out on the text editor that you're given as part of the interview process. Or if you have a piece of paper in front of you, feel free to draw it up and hold it to the camera. Your interviewer will be flexible with you, as obviously we all understand the challenges of interviewing remotely. So those are 3 approaches to the actual problem being asked, the LRU cache, and then one kind of approach 0 that wasn't necessarily the question that we were asked, but it was a similar question. It was kind of a simplification of the question to get us started thinking about the problem. And I hope what you gain from this is the understanding that we didn't have to have the right answer right away. And even if we had stopped on any of the approaches before this final approach that had O of 1 operation for get and insert, we would have still talked through a lot of the different elements to the problem with the interviewer. The interviewer still would have seen a lot of our thought process as a candidate and still collected a lot of data about the considerations we were making and the data structures we were using and why. If this were an actual interview, I would have spent more time talking about my choices of data structures. So for instance, I would have spent a bit more time talking about my choice of a linked list or my choice of a hash map. And hopefully the interviewer would understand a little bit more about my thought process that way. So I'm going to end with some common mistakes in coding interviews. And one will be familiar because I've tried to make it a bit of a theme throughout this. If you attempt to implement the perfect solution, it might be perfect and complex. You might not have a naive solution working first. That can be a really common mistake. It can lead to people getting stuck or making the problem more complex than it needs to be. And if your logic is difficult to follow both in code and in communication, we'll have a really tough time as an interviewer being able to understand your perfect complex solution in the first place. A second common mistake is not mentioning or considering edge cases. It is okay to initially mention them and then come back to them later or write the code that handles them after the fact. So like I mentioned, if I were to solve this problem in an interview context, I would probably do some doodles, some sketches drawing out a linked list, drawing out what it looks like when I walk through the problem with some example input, and making sure that I'm catching all of those edge cases or different problems that might come up with different inputs.